Sample problem number 4 of internal force convection. So for problem 4, we're given with water. So this is in English unit now. 40 degrees Celsius. And then the properties for this water at 40 degrees Celsius are given as density in terms of pound mass per feet cube, and then the dynamic viscosity, pound mass per feet per hour. And this water is flowing in this pipe with a diameter of 0.15 inch. And then this is 30 feet long pipe. So this is a circular tube. And then the average velocity of the water is 3 feet per second. So determine the pressure drop and then the pumping power requirement to overcome this pressure drop. So again, fluid flows because of change in pressure. So when there is a pressure drop, pumping power is also required to overcome this pressure drop. So what is that pumping power that is required to overcome the computed pressure drop? So these are some of our assumptions. We have the flow is steady and incompressible. So we maintain the density of the water at this level, and then the entrance effects are negligible. Thus the flow is fully developed. So meaning at this analysis, we already consider the flow to be either laminar or turbulent, whatever the type of flow is. So it's already fully developed. The entrance effects are no longer considered. The pipe involves no components, so there is no bends, valves, or any other connectors. So the properties of the water are given. So these are already given. Density, dynamic viscosity. So we just need to convert this dynamic viscosity to seconds. So divide this value by 3,600. That's why we have this value. So looking at for the formula for the pressure drop at page 27 of our material. So this is our pressure drop. But something is missing in this formula. We need to multiply this with the friction. So the F. So we will look for the value of F, and it actually depends whether the flow is laminar or turbulent. So it has different formula for laminar and turbulent. But generally the formula looks like this. We have the length, the diameter, and then the density, the velocity divided by 2. And then for the power, pumping power required, we just multiply this delta P, the pressure drop, by the volumetric flow rate of water. So this is our working equation in finding delta P. So F, L over D, density, Vm squared over 2. So looking at these values here, we are lacking with F. We already have length, that is 30 feet. Diameter, that is 0.15 inch. Just convert this one to feet divided by 12. Then we have density is already given. Velocity is also given. So we're just lacking with F, the friction. Friction is unknown. So we need to solve for the value of the friction. So the friction is dependent whether the flow is turbulent or laminar. So again, to evaluate whether it is turbulent or laminar for internal force convection, we need to solve for the Reynolds number. So Reynolds number. So the Reynolds number, if you can still recall, so the formula for Reynolds number. So this is the formula for, again, Reynolds number is our criteria in identifying whether the flow is laminar or turbulent. So the formula is given as density times average velocity times diameter over dynamic viscosity, or when you don't have these two values, just look for the table for the value of kinematic viscosity. So this diameter here is equal to the diameter of the tube if the tube is circular. B average here is the average velocity. However, for non-circular tube, just like this one, rectangular duct, we have a different formula for finding the D. We will look for dH. So that's equals to 4AC over P. AC is the cross-sectional area. The cross-sectional area, so this one, this part here, divided by the perimeter. So also the perimeter enclosing this area. So laminar flow if RE is less than 2,300. Turbulent if the RE is greater than 10,000. So we need to solve for the RE to determine if it is laminar or turbulent. So let's solve for the Reynolds number. So substituting the values for density, the average velocity, diameter, and then the kinematic viscosity. So we need to convert diameter to feet. That's why we have this one here, conversion. So our Reynolds number is actually 2,250.721, and this is less than 2,300. So if it is less than 2,300, the flow is laminar. So let's look for the formula for finding F if the flow is laminar. So for laminar flow in tube, circular tube, again the Reynolds number should be less than or equal to 2,300. For circular tube, the friction factor is given as 64 over the Reynolds number. So this is our formula for finding F. So since we already computed RE, we just divide 64 by RE. So F is therefore 64 over RE. So substituting to our original equation in terms of Reynolds number, so F now will become 64 over RE. Substituting 64 over RE, so RE, and then the other values that are already given. So take note that our value should be in terms of pound force. If you're going to look at these units here, the units will be in terms of pound mass. So remember that delta P, our pressure, is force per unit area. So it must be force. So we need to convert pound mass to pound force, and this is the conversion. 1 pound force is 32.2 pound mass feet per second squared. And as you can see, we can cancel out some values here because of this conversion. So we can cancel out this one, and we can also cancel out 1 feet, then the second squared. So leaving us with, substituting all the values, leaving us with pound force per feet squared. So this part here will become feet squared times feet, so that's feet cubed. Feet cubed divided by feet is equals to feet squared. That's why we have pound force per feet squared. And to have a value that is equals to PSI, so just convert again feet to inch squared, so that we have pound force or pounds per inch squared, or PSI. So our delta P in PSI is 4.13 PSI. So this is our pressure drop. And And then for the power, so we know that the pumping requirement can be computed in terms when you have volumetric flow rate. So our volumetric flow rate in thermodynamics, it is, the symbol for that is Q. But now, to avoid confusion, Q is equals to AV. So now this is V dot. So our volumetric flow rate V dot is equals to area times the velocity. So the velocity times the cross-sectional area of the tube. So velocity times pi d squared over 4, we can get the volume flow rate of the water. Substituting this value here, so we can have this one. So our pumping power is delta P times Vm times the area of the cross section. And then substituting the values which we already have. So we will go back to the value of feet squared so that our values here will be consistent feet. So if you can look at it, the resulting unit for this one is pound-force feet per second. So we need to convert it to watts so that we can have an SI units. So this is the conversion factor of pound-force feet per second to watts. So that's why we have 0.2974 watts.